In this lesson, we will derive the differential form of the conservation of mass equation, which is often called the continuity equation. On the right, we have a fixed, non-deforming control volume that contains a fluid. The control surface is indicated by red dashed lines. We now apply the general conservation of mass equation for a fixed, non-deforming control volume. The time rate of change of mass in the control volume plus the net flux of mass across the control surface is equal to 0. Let's examine the first term, which is the time rate of change of the integral rho dv, where the limits of integration are the entire control volume. Since the control volume is fixed and non-deforming, the limits of integration are constant in time, allowing us to move the time derivative into the integral. The first term becomes partial rho partial t times the differential volume dv, integrated over the entire control volume. We had to change the full derivative to a partial derivative because density can be a function of both time and space. The second term in the conservation of mass equation is rho times the dot product of the velocity vector and normal vector times dA integrated over the control surface. We will convert this surface integral to a volume integral using the divergence theorem, which is also commonly called Gauss's theorem. The divergence theorem states that if G is a vector field that is continuously differentiable within a region of space, such as this control volume, then the following relationship holds. The dot product of G and normal vector n times dA integrated over the entire control surface is equal to the divergence of G times dV integrated over the entire control volume. If we substitute rho times the velocity vector v for G, the left side of the divergence theorem is the same as the second term in the conservation of mass equation. So we can replace the surface integral in the conservation of mass equation with a volume integral. Since both terms in the conservation of mass equation are now volume integrals over the same region of space, we can combine them into a single integral. The integrand of this integral is the quantity partial rho partial t plus the divergence of rho times the velocity vector v. This integral equals 0 for any control volume you could think of. Whether that control volume encompasses a region of space outside our original control volume, or if the control volume encompasses just a part of the original control volume, or if the control volume encompasses a much larger region of space than the original control volume, or if the control volume encompasses an infinitesimally small region of space. The only way this is possible is if the integrand itself is equal to 0. If this weren't true, and the integrand is non-zero in a certain region of space, we could simply form a control volume around that region to obtain a non-zero value for the integral. We now have the continuity equation, which is the conservation of mass equation for an infinitesimally small region of space. It is valid for all points in space for steady and unsteady flows, compressible and incompressible flows. There are a couple special cases that arise frequently in fluid dynamics. The first case that we will examine is incompressible flow, in which the density does not change significantly in the region of interest. This means that the time rate of change of density is equal to 0. Additionally, the density can be pulled out of the dot product since density does not vary in space. Dividing both sides by density, we find that the divergence of the velocity field is equal to 0 for incompressible flows. If we expand the divergence of velocity, we obtain that the sum of partial u partial x, partial v partial y, partial w partial z is equal to 0. The second special case is steady compressible flow. For steady flows, the density field is constant in time, so the time rate of change of density is equal to 0. However, density may vary in space, so we cannot pull density out of the dot product. The continuity equation becomes the divergence of density times velocity is equal to 0. Expanding this term, we obtain partial rho u partial x plus partial rho v partial y plus partial rho w partial z is equal to 0. Looking at the big picture, the continuity equation relates the density field and velocity field in a single equation. However, there are 4 unknowns in this equation, density and the 3 velocity components. These variables may vary in time and space. Many flows can be approximated as incompressible, which simplifies the continuity equation and removes density as an unknown. But we still do not have enough equations to solve for all of the unknowns. In order to determine the velocity field, as well as pressure field, which is often useful, we need more equations. The conservation of linear momentum equations, which are also called the Navier-Stokes equations, are required to help us solve for the velocity components and pressure at all locations in a flow. The Navier-Stokes equations will be derived in a separate video.